An extremely helpful theorem is going to be the argument of this lecture. This theorem is called Grassmann Theorem. A version of the Grassmann Theorem states that the dimensions of the kernel and image of an homomorphism are strictly related. See lecture 9.1 for the definition of kernel of homomorphism. It is basically the pre-image of the zero vector of the codomain. That's the definition of a kernel of an homomorphism. Theorem: let f from V to W be an homomorphism and the dimension of the domain less than infinity, so a finite dimensional domain. Then the dimension of V equals the dimension of the kernel of f plus the dimension of the image. And you can see that typically one has the dimension of the domain and tries to compute one of these two dimensions, dimension of the kernel and dimension of the image, and by this relation we can derive the other. And this very strict relationship that must hold between these three positive integers has striking consequences for homomorphisms. This is probably the most important result we will cover about homomorphisms. The most important being the isomorphism theorem, which has the Grassmann theorem as a corollary, has this statement as a corollary. But we will not talk about the isomorphism theorem here. While for a set theoretic map F, injectivity must be checked counting elements in the pre-image of every element in the image, the Grassmann theorem implies that it suffices to check in the pre-image of the zero vector. Let's see what this statement is about. So let's say that V is a set and W is another set, and we have a map F from V to W, just a set theoretic map. So V and W. Let's say that this is the image of F. Remember that injectivity of a map means that if I start from two elements in the domain, their images will be different elements in the codomain. If there exist two elements in the domain that are going to are mapped to the same element in the codomain, then the map is not injective anymore. Equivalently, to check injectivity, I need to take any element in the image and see what's the set of all the elements that map to this element here. So if we start and we call this Z in the image, this set by definition is denoted by F minus 1 of Z, which is called the pre-image of Z. Now injectivity is equivalent to the fact that these pre-images all contain just one element for every Z in the image. If there is one element in the image whose pre-image contains two or more elements, then the F will not be injective by definition. For set theoretic maps, checking that the pre-image of one element contains just one element is not enough to conclude that F is injective, because we have to check that this holds for the pre-images of every single element in the image of F. This is not true for homomorphisms. So let's draw here the vector space situation. We have again V, and we have W. We have the image of F. F now is a homomorphism. This is f of image of V, image of f. Certainly we have the 0 element of W in this image because every homomorphism sends the 0 vector of V in the 0 vector of W. The pre-image of the 0 vector of W here is by definition the kernel of F. What we are going to see in the following statement is that F is injective if and only if the pre-image of just the 0 vector contains just the 0 vector of V. So the pre-image of the 0 vector of W contains just one element. It suffices that I check this for the pre-image of the 0 vector of W. I don't need to check it for every pre-image of elements in the image of F. If this is true for the 0 vector, then it is true for any other vector of the image of F, and also vice versa. If it is true for, doesn't need to be the 0 vector here whose pre-image I'm looking at. It can be any other element. Okay, but the statement we will see is, we will prove it just for the pre-image of the 0 vector. So this is what makes the difference between a homomorphism between vector spaces and just a simple set theoretic map between sets. Set theoretic map between sets can behave in a completely unrestricted way, whereas homomorphisms have pre-images of elements in the image, pre-images that are all sets with the same cardinality. There is a very explicit bijection between all the pre-images of elements in the image of F, and F acts sending all these pre-images to individual points in the image. Therefore, V can be decomposed and can be partitioned with these infinitely many classes. Usually all of them have the same cardinality. Corollary: let F be an homomorphism, then F is injective if and only if the kernel of F is 0. This is just a corollary of the Grassmann Theorem that we stated before, and I anticipated what it means by the discussion we just had. Proof: it is an if and only if, therefore there are two implications we have to prove. One is the statement that we get assuming that F is injective, and we want to prove that the kernel of F is reduced just to the identity element in V. While this is true by definition of injectivity, as just mentioned, F is injective, set theoretically injective, if and only if the pre-image of every element in the image of F comprises just one point, one element of V. Well, in particular, this must hold for the pre-image of 0 in W. Therefore, this is just a part of the definition of injectivity. What it is non-trivial is the opposite implication. So, assuming that kernel of F is 0, we want to prove that F is injective. So, just looking at the pre-image of the 0 vector in W, we can see whether every other pre-image of W contains just one element or not. So by the Grassmann theorem, we know that using the assumption that kernel of F is 0, the dimension of the domain equals the dimension of the image. Now, in order to show that F is injective, I will define a map going from the image of F, that is contained in W, to V, such that the composition, let's call this map G, G composed with F is the identity of V. Let's draw a picture. Here I have V, here W, and then I have f that goes on to its image f of v, and I want to show that f is injective by defining a g such that the composition of f with g is the identity on f. So if I first take f and I go here, and then I take g and I go backwards, I obtain the identity on v. The g will be defined just on f of v. It will not be defined on all w. Okay. Why is this true? Let's assume that f is not injective, under the assumption of the existence of g with this property. Then what happens? If I start with two different elements in the set in the domain V and apply first f and then g to these two elements, I will be getting again these two different elements. So the first element will be going to the same one, and the second element will be going again to itself, because g composed with f is the identity of V. If by any chance f sends these two elements in a unique element in its image, then what happens is that g cannot send this unique element to these two different elements. G it is a map, so by definition of function cannot send a unique element to two different elements. G must be sending this unique element to some unique element of V, contradicting the fact that f composed with g is the identity. Let vi be a basis of V. Then the images of the elements vi in the codomain, namely f of vi, is a set of generators of image of f. This is always true, doesn't need any assumption. This is always true for any homomorphism f. Let's prove that besides being generators, they are also linearly independent. F of vi's are also linearly independent. We use the corollary of lecture 5.4, which implies corollary of lecture 5.4 says that n generators of a vector space of dimension n are linearly independent. So we will use this fact. Now let n be the dimension of V, which is also the dimension of image of f, dimension of image of f by the Grassmann theorem. Now I claim that the set of the images of the bases f of the vi contains n vectors. Okay, it cannot contain more than n vectors because the vi's are n vectors, so their images cannot have more than n vectors, cannot be a set of more than n vectors. If it has a lower number, strictly lower number than n vectors, what happens is that image of f will be generated by a number fewer than n of vectors. But image of f has dimension n. So it cannot be generated by a number fewer of n of vectors. Therefore, f of vi's, since they are generators of the image of f, they must be at least n. It cannot be more than n, so they are n. So the cardinality of f of vi of this set is n. We can therefore apply the corollary, because we have a vector space of dimension n, which is the image of f. We have n vectors n vectors that are generators of image of f, which are the f of vi. Therefore, they are linearly independent. We are in the following situation, then. We have v, and then we have w. We have f that maps v to some subspace of w, f of v. And then we have a certain n vectors here, which are images of a basis here. And these n vectors that are f of vi's are a basis of the image. Now, if you want to define a homomorphism from this subvector space, image of v, to anywhere, we just need to assign the images of these n vectors here, since they are a basis of this subvector space. So to define G, we just need to say where these vectors go in V. And of course, we will be sending each of them to the element they started from. So if this vi goes to f of vi, this f of vi will be sent back to vi for each I. Let G be the homomorphism defined by G of f of vi equal to vi. Well, such G has the claim property because G composed with f is still an homomorphism from V to V, sends an image of vi to itself. Therefore, it is the identity on all the vector space. And this shows that G is the inverse of f as we defined here. Grassmann theorem, as I mentioned before, is very important for its corollaries. We have seen one. Now let's see another one, which is quite striking in his statement. Again, we start from any homomorphism f from V to W, and we assume that the dimension of V equals the dimension of W, and both of them are finite. Then we have the following chain of equivalences. F is injective if and only if f is surjective, if and only if f is bijective. Therefore, injectivity, which usually is completely unrelated to surjectivity, in this case are equivalent. Of course, we have to use the extra assumption that the dimensional domain and codomain are the same, besides the fact that f is no homomorphism. Proof: by the Grassmann theorem, the dimension of V equals the dimension of f of V in this implication, because we are assuming that f is injective. So f is injective, we have seen kernel is 0. And by Grassmann theorem, this implies that the dimension of the domain equals the dimension of the image. But the dimension of the image is the same as the dimension of the codomain. Therefore, since the image is a subvector space of the codomain, the two must coincide. F of V equals W. And this proves that f is surjective on W. To prove this implication, we are assuming that f is surjective, and we want to prove that f is bijective. We just need to prove that f is injective, because bijective means being both surjective and injective. So this implication reduces to showing that f is injective. By the Grassmann theorem, the dimension of the kernel of f is 0. Well, that implies, why is that? Because Grassmann theorem says that the dimension of the domain equals the dimension of the image plus the dimension of the kernel. But we know that f is surjective, so the dimension of the image, the image equals the codomain, so the two dimensions are the same, but the dimension of the codomain equals the dimension of V. Therefore, we have that dimension of V equals the dimension of f of V plus the dimension of the kernel, which must be 0. So the dimension of the kernel is 0 if and only if, of course, the kernel of f is the 0 vector. And while that we have just shown before, that saying that the kernel of f is 0 is the same thing as saying that f is injective. So f is bijective. Last implication is f is bijective implies f is injective. Well, this is just part of the definition of f being bijective. In order to effectively exploit the Grassmann theorem, we need a way to determine one of the two positive integers, dimension of the kernel, or dimension of the image of f, in order to derive the other integer by means of the theorem. So knowing one means knowing the other, since we are assuming that we know the dimension of the domain. In general, computing dimension of the kernel of f requires a solution of a homogeneous system of linear equations. So it requires kind of certain amount of computations to be determined. The dimension of the image of f, however, in general, is little bit less tricky, in the sense that pretty often the map F can be defined as by its associated matrix. It is not rare that the map F is something like multiplication on the left by a certain matrix, going from a Euclidean vector space Rn to another Euclidean vector space Rk. In that case, the dimension of the image of F is immediately computed because of the following remark. Proposition: let f that goes from a vector space V to the vector space W be an homomorphism between finite dimensional vector spaces with basis Vj's of the domain and Wi of the codomain. Then the dimension of the image of f equals the rank of the associated matrix of f with respect to these two bases. Therefore, when we have this matrix from the data that we start from, computing the dimension of the image is much easier than computing the dimension of the kernel. And this Grassmann theorem immediately gives us the dimension of the kernel without actually finding the kernel as a vector space.